All right, we're ready to go. All right, so in the last lecture, I was covering the longest sequence or the sequence with the maximum sum, and we started from an n cube algorithm, then we went to a n square algorithm, and then we went to a n log n algorithm, right? Again, my intent is the problem is not important right now. What's more important is the methods which we are using to slowly reduce the time complexity, right? And as you can imagine that reducing from an n cube to n log n is a significant reduction already in the amount of time requirements. Today what we are going to do is we are going to try to look at how do we reduce it even further from n log n to n. And again, there are many sequential methods to do that. My goal is to try to teach you right now the divide and conquer paradigm of trying to break a problem into smaller subproblems, solving the subproblems, and then merging them together, right? So, we saw one example of that in the algorithm which we discussed last time, is that we said, look, what we will do is we will take a sequence, right, of positive and negative numbers, we will divide that into two parts, we will find the maximum on this side, we will find the maximum on this side, right, and then what we will do is we will look for the sequence which starts from this side and ends on this side, and obviously the overall maximum is nothing but the maximum of all these three sequences. I know that many of you are coming from other classes. I would really appreciate if you try to reach here in time, because otherwise we keep getting disturbed again and again. All right. Let me ask you quickly, do you have a class before this one, which in the period just before this? How many of you have a class just in the period just before this one? So, I have some idea of what are the dependencies which we are working with. Do you have a class in the period just before this one? Any of you? No. So, in that case, it is even more important that you come here on time, right? We start at 10:35. It is only a small lecture. If people keep on coming late, we will only start a little bit later, because clearly everyone gets disturbed, right? Yeah. Is it 10:35? I thought, no? Oh, I'm sorry. Okay, so it's my fault. Okay, so obviously I was mistaken about the start time. I was assuming it was 10:35. So we are all set then. Okay, good. Problem solved. All right. Let's wait for a few more minutes in that case, since really this is not the official start of our lecture so far. Do you have any questions from the last lecture? Yeah. Any questions about administration? I will have the list of 4 or 5 TAs on my website today. They were still finalizing because the course schedules were, the number of enrollments were changing. So, finally they have figured that out, and we should have the TAs for this course starting today. All right. Let's see, maybe wait for another minute, because we don't want to start early. You have any questions which I can answer till we start? All right. Okay, maybe we can start a minute early today. So, what we were talking about in the last lecture was the divide and conquer paradigm, where you take a list, you divide it into two parts, you find the maximum on the left side, maximum on the right side, and we know that there can be sequences which start from the left and to the right. In that case, you have a sequence something like this, and we take the maximum of these three. And the way I described the problem to you last time was that the time taken T n is nothing but solving these two sub problems, because essentially you are applying recursion, each of which will take obviously 2 times T n over 2, and you can say, well, what happens if n is an odd number, right? For now, we will assume n to be a power of 2. It is a simplification. One can easily show that many of these recurrence relations which we will develop in the course will work even when you have n to be a odd number or not a power of 2. It gets into more detailed theoretical computer science, which I think is beyond the scope and value for this course. I think it is more important for us to learn techniques rather than worrying about some of these details. So, T n is equal to 2 T n over 2 plus obviously the time to find the sequence, and as I discussed at the end of last lecture, what I can do is, what I showed to you was that I can divide this into two parts, and this sequence is nothing but the maximum of all the sequences which start at this and end somewhere here. So, I look at all of these and pick the maximum of this on this side, and the same thing on the other side. I just sum them up and I get my maximum sequence which starts from the left and the right, and clearly starting from this side, all I need to do is add this, I add the next, add the next. I go through a simple scan starting from the right and to the left. That scan takes me n over 2 time on this side. I find the largest one on this side, n over 2 scan on the other side gives me the largest one on the other side. I sum them up, I got the maximum sequence between the two. So, but the time requirement for that is proportional to the length of the sequence. So, this becomes some constant times n, and you can bicker about it and say, look, you forgot to take the maximum of 3, that will take another constant maybe 3, but most of the time what we will do is we will just say, look, I can always absorb this by choosing a large value of d, because still n is greater than 3. This will I'll instead of using c equal to 3, I'll use c equal to 4, and it will work out fine for me, right. So, generally speaking, we will make those approximations. Again, if you really want a detailed analysis, you can always go and do it, and you will check it, you will find out that actually it works out fine, all right. So, this is the equation, and then if you remember, I drew this nice tree, and we did level by level summations. We found that each level took Cn amount of time and the log n level. So, time taken was Cn log n. But now our goal is to be able to reduce this to something which is some constant times n. Now, can we do better than linear? Before we start, let us see, are we setting our goals too low? Maybe you can come up with an algorithm which it takes square root of n time. Is that possible? Anyone? So, if you have n elements, can I have a sublinear algorithm in n? Is that even possibility? We should even, because we are trying to set our goals to be maybe too low, maybe we should aspire for a square root of n algorithm. So, most likely that is not possible. Why?
For n elements, sequence of length n, so how we can do by exploring less than n?
So, I mean, I guess you need to be precise about it, right? You can't just say, oh, well, how is it possible to sequence of length n, how can I do better than n? Because there are algorithms like binary search, and we will discuss some of that, where we can actually do log n time, right? So, the argument is very simple, right? If I skip one element, that may be a really large element or a really negative element, then I may miss the largest sequence. So, any algorithm which does not look at every element is most likely going to make an error, because I can make that number to be very, very large or very, very small. So, whatever sequence you find, that number could be the largest sequence, or if you skip that particular number, then if I am including that particular number in a sequence, if I make the number to be highly negative, then that sequence could not have been the largest one. So, what that simple argument tells you, again, this is not a very, very precise theoretical argument, but a reasonable argument, which basically says that any algorithm to find the longest sequence, or to be more precise, the sequence of the maximum sum, should look at every element at least once. That means, if you have to look at every element at least once, it will take you at least n amount of time. So, no algorithm for this problem can be solved in less than n time. So, now let us try to see how can we actually go about reducing the time from n log n to n, right. Okay. Remember this, now this was dn, right. Okay. This was dn. We need to somehow reduce this amount to something smaller than dn for it to be able to be an algorithm which is less than dn log n, because for dn we showed last time that every level was n amount of time and there were log n levels. So, now we need to come up with some way of finding this sequence which starts from here and ends there in something which is less than order of n time, because if it takes order of n time, whether instead of taking dn it takes dn over 2, it is not going to make a difference. All that will happen is the d will get replaced by d prime, where d prime is a smaller constant than d. That does not really help us much. So, we need to come up with so here is what I am going to do. Suppose I have an algorithm which does the following, right. So, I am going to calculate 4 things, right. I am going to calculate sum is nothing but sum of all the numbers in the sequence. So, clearly that is nothing but if I need to just sum them up, I just sum them up, right. then what I have is the max. So, there is a maximum sequence which I have in that list or sub list or the whole list, whatever. My goal is to find max, right. My goal is not to find sum, but my goal is to find max. Then I am going to define something called L max. L max is nothing but the sequence which starts at the leftmost point and has a maximum sum. Just for my convenience, I am defining a L max. All right. So, what I am saying is L max is nothing but something which starts at this point and ends somewhere here. Now, my goal is not to find that sequence, but suppose my goal is to find that sequence, I am going to compute that. Similarly, I can define something called R max. What is R max? R max is nothing but something which starts from the right hand side, and I scan from the right hand side all the way to the end, and I compute that sum. Now, it will become clear to you what I am doing, why am I doing this in a few seconds. But what we are dealing with was, we are looking at a sequence which is of length n, right. So, I will divide this sequence into two parts. I will divide the sequence, one on this side and the other one on the other side. So, I divide it into two parts. So, basically what I can do is, recursively I will compute all those 4 values for the left side, and I will compute those 4 values for the right side. So, what will happen is, I will effectively have sum of L, max of L, L max of L, R max of L, right, for the left sequence, and I have the same quantities for the right sequence. So, what I have is sum of R, max of R, L max of R, and R max of R. Now, let me make sure that you understand this. What does L max of R mean? R corresponds to the subscript, R corresponds to the right subsequence. L max basically is something which starts here, I start scanning and has a maximum sum over all the sequences which start somewhere right here. How about L max of L? This is nothing but something which starts here, goes up to this point, right, only for the left sequence, right. We are only talking about recursively defining these terms. Similarly, what is R max of L? R max of L is nothing but something which starts here and goes, if you scan, take the maximum of them. Now, suppose I recursively compute these quantities, right. So, what happens is, if I am solving a problem of size T n, I first solve 2 sub problems of size T n over 2, where what I do is I go ahead and compute these quantities. So far so good? Any doubts? Any doubts about the terminology? Raise your hand if yes, go ahead. So, max L is the maximum sequence, subsequence here in this. Max R is maximum subsequence in the right hand side. Our goal finally is to compute this max sequence, right, or sequence with the maximum sum, right. Okay. So, this is that sequence basically. All right. Just to avoid any confusion with the word max, if you want to call it max S, that is fine with me, but at a high level, max is the sequence which is what we are really looking for. Our goal is to basically find this basically, right. Our goal is not to find anything else. We are looking for the sequence with the maximum sum. All right. So, now let us see, suppose I told you that, okay, I called a recursive algorithm which solved this problem for you, solved this problem for you, each of them will take T n over 2 time, right, because you are working in half the problem size. Okay. So, I added 2 T n over 2, but now I need to add some time to figure out all these values from this. Now, let us look at it, right. What is sum? Sum is nothing but, sum for the entire sequence is going to be nothing but sum of the left side plus the sum of the right side, right. It is very simple. Sum of the entire sequence is nothing but, if you already know the sum of this, you already know the sum of this, rather than trying to add them up all again, I can just add those 2 values, correct. So, I can easily say that sum is nothing but sum of L plus sum of R. Correct? So, if I know this the sequence sum of, so suppose this was 1 2 4 7 minus 2 5 8 3, I will sum each of them separately in the recursion, and then when I bring it up I will just add them up together. I do not need to do it. How much time does this take? This takes basically constant time, right? All you are doing is one add, nothing more than that, right? It is very fast, but this is very simple. Now, go ahead. Okay. So, now let me look at the easier ones first, and then we will come to the max part, right? How about the L max? What is L max? What is L max is telling? L max is saying, now I need to look at the entire sequence which starts here and ends there, right? Okay. That entire sequence I am looking for the so now the two scenarios, that sequence which is starting here can end here, right, or it ends somewhere here. I do not really know beforehand which one it is, right. Now, if it ends on this side, then that is the same as my L max of L, all right. But there is also a scenario which I do not know where the sequence ends there. Now, if it ends there, what can I say? What will be this value? Go ahead. So, sum L plus L max of R, because what you are saying is, look, if it is ending here, this better be the maximum among all of those values. That is nothing but my L max of. So, the other option is, it is sum of L plus L max of R, and the maximum, if I put the maximum of these two, I am covering my bases, right. So, I do not know which one it is. I will try this one, I will try that one, take the maximum of the two. How much time will this take? This will also take some constant time. In this, say 3 or 4 operations, I will be done. So, if this takes 1 operation, maybe this will take 3 operations, maybe 4, does not really matter, right. Okay. Clear so far? Yeah. So, the right part basically saying is the sequence is ending from here to here, right, and this is the maximum. That means, this is the maximum of all sequences which are starting from here, ending somewhere on this side, correct. All of those sequences will obviously have all of this in there, that sum of L, and plus among all these sequences, if I already know that this sequence has the largest sum, right, then I might as well use that, because there is no point me wasting my time trying to reevaluate all of them again, and that is all this is saying. Okay. How about R max? R max is just the other way around. I am starting from here and going this way, right. So, can someone tell me the expression for that? So, from whatever I can hear from this, this is nothing but the maximum of R max of R sum of R plus R max of L, correct? All right, the same argument, just the mirror image of the same argument. Again, I can compute this in 3 operations, right, or 4, does not really matter. Okay. So, I am doing 1 sum and 1 max, so you can count it as 2, 3 does not matter, right. Okay. So, now the key part was my goal was to find max. This other stuff I was just doing on the side, right, just to make my life easy. What will be the max? If I write it here, can you guys see it clearly, or that's too low? Too low? Okay, good. All right. So, let us write it here. So, max will be nothing but, now remember, max is either the max is coming from the left hand side, or the max is coming from the right hand side, or the max is coming from something which starts on this side and ends on this side. So, I clearly know that max is nothing but, and I am going to use a small max just to not confuse you, is nothing but max of L comma max of R comma. So, this covers the either the sequence belongs completely on the left side or completely on the right side. Now, I need to start the other third scenario is I start somewhere here and end somewhere here. So, it will be nothing but R max of L plus L max of R. All right. All I am saying R max of L is nothing but something which starts on the left hand side, it starts from here and goes all the way here, the maximum of that. L max of R is nothing but something which starts here and the maximum along that. Correct? How much time does this take? Again, suppose this takes 3 operations or 2 operations. So, let us for the timing assume that each of these take instead of 3, 2 operations. Each of these takes. This one will take 1, 2, taking the maximum of 3 plus 1 add, may take 4 operations, right? All right. So now overall time, if once I have now Tn, I solve the 2 sub problems in time, Tn over 2. All right. And to combine them together, how much time does that take? Some constant time, which could be 7, 8, 9, because 1 plus 2 plus 2 plus 4 is 9. I will just put that as a constant c, which c could be say 10 for example, right, or 15, does not really matter to me, right, some constant. So, basically now what I have been able to do is I am saying that if you are able to solve these 2 sub problems, I am able to combine them together in constant time, which is a lot better than what I was doing before. Basically what I have done is I have come up with a clever way of computing this sequence and this sequence also recursively. Before I was actually scanning from left to right, right to left. Now I have come up with a clever way of actually computing those recursively too. So, that way I can save some time. So, now what happens is I have Tn equal to this plus this, but I still need to solve this equation, right. Before I go and solve this equation, I want to make sure that you understand this. This is basically saying that this is the sequence, if the sequence is completely on the left or completely on the right, or it starts on the left and ends to the right, then this is covering that. And this is what we did last time. The only difference is we actually are computing these 2 values now recursively, so that by using this formula right there, so that we do not have to spend the linear time for scanning from right to left or left to right, and that way we are able to save time. So, now this is the formula which we need to solve. Let us try to solve this. If you look at this, this basically is saying that if I have a problem of size 16 for example, right, then once I can solve the problem of size 8, I can merge this in constant time. To solve a problem of size 8, I will apply the recursion one more time. Again, to solve a problem of size 8, I would break it up into problems of size 4 and 4. It takes me constant time. Here 4 and 4, it takes me constant time. The next level will be 2 and 2, 2 and 2, 2 and 2. The next level will be 1 and 1. Clearly at level 1 the problem is very straightforward, right. When you have level 1, you can easily compute what is your sum, what is your max, what is your L max, what is your R max rather easily, right. And I want you to go think about it. It is not as easy as I am saying. You need to initialize those values at that level, or maybe you initialize at 2, it does not matter, right. So, now let us compute the total time, right. So, it took us each of this is taking c amount of time, right. This is just to I will circle them so that you do not confuse and say this is 8 c, this is actually all c's. So, how much time am I spending at this level? C, right. How much time am I doing at the next level? 2c. How much time am I spending at the next level? 4c. How much time am I spending at the next level? 8c. And the last level in this case will be 16c. Correct? Now, in general, if you had a problem of size n, what will happen? The top level will be c, the next level will be 2c, the next level will be 4c. What will be the last level? nc. What is the total time? Total time is nothing but nc plus n. I am going to go this way now, right? Okay. nc plus n over 2c plus n over 4c, finally 1c. That is nothing but if I look at this as, if I take NC common, there is nothing but 1 plus half plus 1/4 plus 1/8 plus finally it will be 1 over n. So, it is nothing but 1 plus half plus 1, or you can do it, you can sum either way, it is going to give you the same result, it does not matter. So, what happens is, as we know, the maximum sum of this sequence is how much? 2. So, basically what it is saying is the total time taken is 2 Cn, right. 2 Cn is nothing but theta of n, because it is basically lower bounded and upper bounded by some constant times n. So, now I have a linear algorithm to solve the problem. So, I started with the n cube algorithm, then I went to n square, then I went to n log n, then I went to order of n. Clearly, now this is much faster than whatever we have seen before. Now, if you have a million elements, the time requirement will be proportional to million. If you have a trillion elements, it will be proportional to a trillion. The more important part is that we were able to break up the problem into 2 subparts, solve each of the sub problems smartly, combine the results together to get a solution for the larger problem. Now, just to understand the execution of this, to execute a problem of size 16, I will make calls to 2 sub problems of size 8. To solve this one, I will make calls to 2 of these. To do this, I will solve to do of this. So, in some sense, it is going to be a you will start with solving these 2, then solve this one, then solve these 2, then solve this one, then you combine this to get this one. You will do what is called a in order traversal of this tree to be able to compute the overall algorithm, right, or to compute the longest sequence of, or the sequence of the maximum sum over the entire problem of size n. Any questions on this before? Yeah, go ahead. Uh-huh. Well, so the thing is, if you just do R max and L max, then those only consider sequences which are starting here and ending somewhere here, but the maximum sequence could be somewhere in between too. No, it's only starting from the leftmost point, not starting from the left. So, L max only considers sequences start at 1, right. But the thing is, the maximum sequence could have started somewhere at 5 and ended at 9. Okay. So, L max is obviously not going to cover those sequences. That is the reason we need to do what we need to do. Any other doubts? I am glad you guys are asking questions, because I am sure if one of you has a doubt, there are probably 15 other people who have the same doubt. So, if you have any more doubts, please raise your hand. Yeah.
So, for each of the steps, we need to calculate L max L and L max R.
Right.
For that case, don't we need to traverse the entire sequence from the leftmost position?
No, because what we are saying basically is that once I know, so the whole idea here is to solve a problem of size 16, I am first solving problem of size 8. But actually, to solve a problem of size 8, first I am solving a problem of size 4. So, you need to look at recursion, and I can help you with that. That is a question which I think is somewhat beyond the scope of this course. But when you do the recursion, what will happen is the way it will start actually will be that when you have sequence of size 1. When you have sequence of size 1, computing sum max L max is very easy. So, what you are saying is I am going to first solve problems of size 1, then solve problems of size 2, then solve problems of size 4, then solve problems of size 8, and then solve problems of size 16. That is why we do not have to do the scanning.
So, does that mean that order of n completing the sum or max is implicitly coming under 2 of TL by 2?
Correct, exactly. So, what you are basically saying is, look, the time to compute this overall problem is whatever time is there to compute this one, plus the time to compute this one, which is your T n over 2, plus constant time. So, to compute this one, again you will divide this up into this part, and then the additional time besides solving this is nothing but see same thing at the next level. So, that is why recursion allows us to say, look, I do not worry about how you solve the sub problems. Once you solve the sub problem, how much time does it take to combine, because the time to solve the sub problem is already included in this one. Now, instead of dividing into 2 parts, if I divide it to 3 parts, then I will have to multiply 3 times t n over 3. In general, if I divide it into k parts, it will be, if I am using all the k sub problems, then I will have to do k times t n over k. That will be the time for solving the sub problems, and then you combine them together.
So we can write this equation as like k times t n over k.
In that case, of course. In this case, we have 2, so we obviously have. We'll look at more general forms as we go along. I'm trying to first take simpler problems and solving it, and then we'll look at more complex problems. Any other? Yeah.
C here is only the time to merge the two, or
C here is only the time to merge. So the C is nothing but your 1 plus 2 plus 2 plus 4 for that one. So it's 9, 10, something like that. So basically, bottom line is C is a constant, whether the number is 8, 9, 10, it doesn't matter to us. All that will change is, instead of it being, if I use C equal to 8, it will be 16n. If I use C equal to 10, it will be 20n, but it's still linear in terms of n. Yeah.
Sir, would you like to give a very short summary about the algorithm from the cube to not and until now, the learned path?
Okay. So if you remember in the n cube algorithm, what the n cube algorithm did was, it looked at all sequences which started at any I and any j. And there were how many such sequences? I can take values up to n, j can take values up to n. So there are roughly n square sequences, and then it computed the sum of each of them separately. And each sum could take at an average n over 2 time. So if, since you had n square sequences and you multiplied by n over 2, you got roughly n cube. But we had to do precise analysis to make sure that that is actually correct, and I left it up to you to go figure that summation out, right? In the n square algorithm, what we did was, we said, look, if I look at a sequence that starts at I, if I am looking at I to, suppose I is equal to 5, if I need to go 5 to 6, 5 to 7, 5 to 8, I can do that all in one scan. So that means I can do in order of n all the sequences which start at 5. Okay? So, but the number of such sequences we needed to look was 1, 2, 3, 4. So the time for one was n, time for the next one was n minus 1, the next one was n minus 2, and so the sum of that was n square. The next one was, let's divide the problem into 2 subparts, solve the subproblems on either side, right? But then to actually find the third sequence, we scanned from the middle of the left, went this way, and middle of the right, and went this way, and summed them together. But so that required us time Cn. So the time taken was Tn equal to 2 Tn over 2 plus Cn. And when we solved that recursion, it came to be n log n. All we did here was, we reduced this time of recursion from Cn to some other constant by being clever about using L max and the right R max, and that way we were able to reduce the time. If you have any further doubts, please come and talk to me after class. Okay? All right. So let's move on. Okay. So now suppose, yeah.
See, if, for that example, if we solve the, if we compute only the values of this for the 16, the largest, so won't we get the solution? Means instead of doing a recursion, just compute the values.
Right. So again, I'm not suggesting that there may be many other algorithms to solve the same problem, but all I'm trying to teach you with a simple example is how to use divide and conquer to solve effective problems. My goal is less about right now the solution of the problem itself. Maybe there are better solutions right now, but this is a way to look at divide and conquer approach to solve the problem. Okay? Okay. All right. So now let's say suppose you have a sorted sequence 1, 5, 7, 9, 11, 15, 19, 25. Okay? So you have a sorted sequence. In this case, the sequence is of length 8, but it could be a sequence of length r. And suppose I say search for number 10 in this sequence. Is 10 belong to this sequence or not? Right? Okay? Does 10 belong to this sequence or not? So a simple algorithm will say, okay, let me start here, compare 10 with 1, 10 is obviously larger than 1. So let's move to the next one, let's move to the next one, let's move to the next one. It comes here and says, oh, actually I found a number which is larger than 10. That means 10 does not exist in this sequence, correct? So how much time will that algorithm take? N amount of time. N in the worst case, because if you start from the beginning and you look all the way to the end, then n. Otherwise, most of the time is if you are looking for something like 3, in one step you will realize, or 2 steps you will realize that 3 is not present in the sequence. On the other hand, if I ask you is 1 in the sequence, in one step you will know that 1 is in the sequence. So, basically the best case time is 1, the worst case time is n, and roughly one can make an argument that if you are searching equally for all the positions, the average is going to be roughly n by 2. Okay? We are kind of assuming that whenever we search probabilistically, is equal probability of 1 over n that we will be searching for numbers which are kind of uniformly distributed in this sequence, right, or in terms of position more so than value. Now, clearly this is a sorted sequence, right. If you have used a dictionary, nowadays people do Google to use to find something, but if you have used a dictionary, if you are looking for a word which starts with a F, you do not start from page number 1, go to page number 2 till you find something which starts with an F. You say, okay, F is somewhere in the beginning of the dictionary, 1/3 of the way, I will open it and then try to move my way around. You are basically doing what is called a binary search. And in a binary search, what happens is you take a list and you say, okay, I am going to divide this list into 2 parts. So, you have a list of size n, n over 2 on this side, n over 2 on the other side. And then what I will say is, I will compare the element which, suppose I was looking for 3, I will compare that 3 with this element right here, correct, all right. Now 3, so this is roughly the n over 2th element which I am going to compare against. There are 3 scenarios, right. Either the number which I am looking for is equal to that element, in that case I found it, I do not have to do anything more, right. Scenario number 2, the number which I am looking for is less than 9, in this case it is less than 9, then I know for sure that I do not need to search this side at all, because if the number is less than 9, then I could have I only need to restrict my search to this side, all right. Or if the number turns out to be, for example, if I was searching for 14, in that case I do not need to look at the left sublist. So, basically what I am saying is, after one comparison, either I found the number or my problem has been reduced to n by 2, and then I will repeat the same idea again. So, suppose I was looking for 3, if I find this side, then I will look at this middle number and then again compare with 5, and then I will find out that, okay, somewhere in this list, then I will compare with this and say, oh, 3 does not exist because the left side is 1 is greater than 1, and I can't go any more left of 1 because there is nothing there anywhere, right. So, in that case I will stop at that, or actually I will compare with 1 and they say right hand side compare with 5, and obviously 5 is not equal to 3. So, I am done. So, in this case what I am saying is that if I have a problem of size n, I reduce it to problem of size n over 2, and amount of time spent is how much? Constant time, right. Basically all you are doing is comparing with the n over 2th element, indexing the n over 2th element takes constant time, and comparing with that element takes constant time. So, basically this will take constant time. So, another way to write this will be that T n is equal to T n over 2 plus constant. Now, this is the worst case time, because obviously if you are able to find it in the first go, I do not need to add T n over 2, because in that case I am done. So, this is kind of saying that I am going to assume that I always fail, which is the worst case scenario, so that I keep on solving sub problems of size n over 2. So, in this case what has happened is, I go from n to n over 2 in constant time. Then what will happen in the next step? I will go from n over 2 to n over 4 also in constant time, right. Finally, what will happen is, some juncture I will go from 4 to 2 in constant time, I will go from 2 to 1 in constant time. Once I have at 1, I don't have to, I can't further divide that list anymore. Either it's there or it's not there. I'm done at that juncture. So, this is also a divide and conquer algorithm, in which I divide the problem into 2 subparts, right, and then I looked at either the left part or the right. I don't need to look at both the parts now. That's why instead of having 2 T n over 2, I only have a single T n over 2, right. How much time will this algorithm take? How many such steps which I need to take? I am going from n to n over 2, so every time I am dividing the problem into 2 steps, right? Two parts, right? So it's basically if I start with n equal to 2 to the power k, this will become 2 to the power k minus 1, 2 to the power k minus 2, finally it will become 2 to the power 0, and n is nothing but 2 to the power k. So if I start with 2 to the power k, I divide 2 to the power k by, it will become 2 to the power k minus 1, k minus 2, k minus 3, all the way 2 to the power 0. So basically what I need, how many steps do I need? I need k steps, right? Because essentially after every, if you look at it, it's going k minus 1, k minus 2, finally obviously in fact once I go to 2 to the power 1, I don't need to do any more steps. So roughly k, you can count it as k plus 1, it doesn't really matter, but roughly I need k steps. What is k? Because I know, remember this equation right here, 2 to the power k is nothing but n. So this gives me k is nothing but log of n to the base 2. That means the number of steps required are, in this case, this algorithm is theta of log 2n. Okay? Someone will say, look, why do you divide into 2 parts? Maybe I like dividing into 1/3 and 2/3. Okay? So rather than choosing n over 2, I take my list and I say, oh, I'm going to divide this into 1/3 and 2/3. What's the problem with that? If I get lucky, I only have to search through 1/3. If I get unlucky, I need to search through 2/3. So what happens is, in the worst case, I always have to assume I get unlucky. So instead of the problem going from n to n over 2 to n over 4, it will become n to 2n over 3 times 2 over 3 will be 4 over 9 times n, then and so on and so forth. So what will happen is, in the worst case, I'll always be looking in the larger sequence. In the best case, if I get lucky, then I'll go much faster. So why did we choose n over 2? Because n over 2 make sure that both the sequences are of size n over 2. So the worst case is only n over 2.
Like in most of the problems, like having a binary tree, like works very good.
Uh-huh.
Like, are there any problems in which we can have tertiary trees or something?
Correct. So the question is that in most cases, seems like so far we only covered 2 examples. Using a binary tree or dividing into 2 subproblems makes the most sense. We will look at examples in which we don't have to divide into 2. In some cases, dividing into 2 or more actually would make more sense. So we'll look at some examples of that nature also later on as we go in the next set of lectures. So dividing into 2 is the obvious thing to do, but in many cases dividing into 2 doesn't make, as we will see, actually results in bad solutions, right? Any doubts on this? This is pretty straightforward, right? All right. Any questions on this? So in this case, we only chose one of the subproblems, right? And that is the important part about the algorithm. All right. So let's try to look at, now this was assuming that the sequence was sorted. Now suppose I have a sequence and I want to sort it, right? So if I want to sort it, suppose I have numbers like 5, 7, 3, 1, 2, 8, 9, 0. I want to sort these to subsequences. All right? I'll try to apply the same divide and conquer principle, because my goal is for you to be able to learn that effectively, right? Okay. So what I'm going to do is I'm going to take and say, okay, fine, let's divide these two subsequences, and there is some magic genie sitting somewhere which you give subsequences, it sorts it for you for now, right? So what will happen is you give it to the genie, it comes back and says, okay, the solution for this sequence is 1, 3, 5, 7. Okay. How about the next sequence? It is 0, 2, 8, and 9. All right. So now I have 2 sorted subsequences. I need to now somehow combine them together to get an overall sorted sequence. So what I'll do is the following. I'll take this sequence, I'll take this sequence. I have a pointer here and I have a pointer here. I'll compare these two. Which is smaller, 0 or 1? 0, right? So I'll say, okay, fine. I'll write out 0 and I'll move this pointer to this one. Okay. Now what I'll do is I'll compare 1 and 2. 1 is obviously smaller than 2. So, I'll have 1 here and this will move to 3. Now, I'll compare 2 and 3. When I compare 2 and 3, what happens? 2 is smaller, so I move to 8. At this juncture, I have 3 and 8. I compare 3 and 8, 3 is smaller, then I move this pointer, I compare 5 and 8, the same result, 5 is smaller. Then I compare 7 and 8, I get this smaller. At this juncture, I am done with the left sublist, there is nothing left. I have fallen off the cliff as far as the left sublist is concerned. So, then what I will do is whatever is remaining, so this is also called a merging algorithm. Now, this merging algorithm, how much time will it take? Every time the pointer on the left moves or the right moves, and every time I am outputting one element at least, till one of the sequences end. In that case, I am just copying the remaining parts. This will take n amount of time in the max, because every step I am at least outputting one element. If the right list becomes empty, still I am outputting, or the left list becomes empty, I am still outputting one from the right side. If the right list becomes empty, then I am outputting one from the left side. So, basically this will require n comparisons and n copies of the elements to get this list. Now, the important part was this only worked because this list was sorted and this list was already sorted. If you try to do this, if for example, this number was instead of 9, this was a 1, this list is not going, or just to not repeat itself, suppose this number was 1.5, then this algorithm is not going to work, because what will happen is you will copy 8 and then you will copy 1.5 and this list is no longer sorted anymore, right. So, this only works because these two sublists were already sorted. So, I was guaranteed that when I pick the minimum of the two, that is the overall minimum, and since you copy the overall minimum, now you are looking for the second minimum, and basically again you compare the from the remaining elements, the smallest on the either side, that will be the second minimum element. You have a question?
So why don't we say that the time takes to sort the sequences n over 2? Because actually what we're doing is to combine like half of the elements of the sequence.
So, right. So, but see, every time what we are doing is we compare this with this first, right. That takes one comparison, but now the pointer moves to the other one. So, now you compare this with this, right. Okay. So, in the worst case, it will actually be n comparisons, or n minus 1 if you want to be more precise. We cannot always guarantee there will only be n over 2. It's somewhere between n over 2 and n, we do not really care. That is why I put a number like Cn. So, it will basically take some constant times n amount of time to merge these two sequences, whether C is half or 1 or 0.75, I do not care. So, I can always put a larger number whenever it is convenient for me. I will say C is nothing but 1, for example. So, the maximum number of comparisons n. That is my worst case time. Yeah.
Like, is it possible to merge this like two subarrays like in place?
So, there are ways of doing that, but for now let us not worry about that. Okay. All right. So, someone had a question that can you do it in place, because this requires you an extra amount of space which you sometimes may not have, but let us not worry about that right now. Okay. Any other questions on this? So, now I had a genie before to solve these two sub problems, right. Well, I do not need a genie, right. What I can say is I will use this algorithm recursively, right. So, to solve a problem of size n, what I will say is okay, go and apply the same idea to two problems of size n over 2. The output of those n over 2 sequences is going to be sorted sequences, and then I will merge them. So, what I am claiming now is that T n, to solve a problem of size, to sort something of size n, I need to solve two sub problems of size n by 2, and I will apply the same idea again. So, T n over 2 plus I need to add C n. Okay. So, now I need to solve what is T n. What is T n now? We have already seen this recurrence before, right, when we were discussing the other algorithm, right. Every level was the same amount of time, So, there are log n levels. So, T n is nothing but C n log n. So, T n in this case is nothing but C n log. So, this is nothing but theta of n log n. Remember when we looked at the simple insertion sort, the insertion sort required us n square time. This only requires n log n time. Now, just to give you a quick idea of how the recursion is actually working out, I will just go over this example a little bit more carefully, right. So, suppose we have the same example 15732890, right. So, basically what we needed to do was we needed to sort this one and we needed to sort this one. So, basically there are two sub problems, one which requires 1573 sorting, the other one which requires 2890 sorting, and then you do a merge, correct, right. To solve this one, I will break it up into 1573. To solve this one, I will break it up into 2890. To solve this one, I will break it up into 1573, 2, 8, 9 and 0. Now, obviously sequence of size 1 is already sorted, right. Okay. So, then when I need to merge 1 and 5, the result will be nothing but 1 and 5, 7 and 3, 3, 7, 2 and 8, 2, 8, 9 and 0, 0, 9. Now, what I will do is I will merge 1, 5 and 3, 7. What will I get here? 1, 3, 5, 7. Again using the same algorithm, 1 compared with 3, then 5 compared with 3, then 5 compared with 7, and you get 1, 3, 5, 7. Then you get on this other side, you will get 0, 2, 8, 9, same way. And then what I will do is, I will just what I described to you, I will merge these together, and this will take 0, finally the result will be 0, 1, 3, 5, 7, 8, 9. Again, if you look at it, how much time was spent? This constant time was spent here, because if you only have sequence of 1, there is not much to be done anyway. Then say 2 units of time was spent here, 4 was spent here, 8 was spent here, but there are 2 leaves of 4. So, this is basically the work is nothing but 8 plus 8 plus 8 plus 8. In general, we start with n, you have n, 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 n. So, you have total of n times log of n. So, what we have now is a divide and conquer algorithm for sorting a sequence of length n, and as we will see later on in the course if we have time, that n log n is the best sorting algorithm you can ever hope to achieve, assuming that your algorithm is based on using comparisons. There are other approaches which do not use comparisons, which actually use the values directly. They can be faster, but if you are using comparisons, there is no way we can do better than n log n times some constant. Take a break right here. If you have any questions, I can answer them before we disperse. All right, we will see you on Thursday.